Hey guys, let's discuss new round, which is round second, which is called coding round one, and after this you will have coding round two also, which is called round third. Okay, so here the question is design a rate limiter. So we need to design rate limiter. I have created one video on system design where I have covered rate limiter, what is rate limiting, and then rate limiting algorithm. Okay, like 5 to 6 algorithms we have discussed there. So you can go there and check the rate limiting thing in detail. And here the question is design a rate limiter. Okay, so let's say again we will be talking about so here also okay, we will have a question. Okay, and then we will see we have multiple roles like software engineer, senior software engineer, and architect. So we will see what each role will answer, okay, expected to answer, and which level of answer they required. Okay, and then after that we will be taking some follow-up questions like 10 questions, okay, on that particular thing. So we will be discussing in detail. So the question is design a rate limiter. So let's say if you are a software engineer of 3 to 6 years of experience, okay, if you're a senior software engineer, then like 7 to 12 years of experience you can say, and after that above you will be having the role principal software engineer or architect. Okay, so let's say if you're a senior if you're a only software engineer 3 to 6 years, okay, so see what is the expected answer. Okay, so you will say that before jumping into coding I would clarify few requirements. See, this is the system design question, okay, and also coding as well, because you need to code here, and so you need to clarify a few requirements, correct? So what would be those requirements? See, is the rate limiter limit per user, IP, API key, or tenant? Okay, so if you don't know what is rate limiting, so let's say you have an application and user is requesting, okay, to your application. Now user can request anything, right? Like number of users can use your application, or let's say there is some hacker, okay, there are few hackers. So they will they will send a lot of requests to your application, like let's say lakhs of requests or something, so your application will be down. Okay, so to prevent all these things we limit how many requests we will be processing from per user, or per IP or API key or tenant. Okay, so tenant organization, your application can serve tenants also, or different organizations as well, right? So first you need to clarify that I need is the rate limit per user, per IP, okay, or API key or the tenant. Now the second thing is how many requests are allowed, like 100 requests from each user, okay, from one IP 3 requests in 1 second, or 10 minutes or something like that. Now what is the time window, like in 1 minute I will accept 100 requests from particular IP, right? So that time window. And then is this a single server application or a distributed server? So you are sending requests to one server only, or you have a multiple request distributed system and then you're sending the request there, right? So for a single server implementation, I would use an in-memory concurrent hash map where the key is the client ID, and the value stores the request count and window start time. Okay, so what he will be using? He's saying software engineer is saying he will be using concurrent hash map. Okay, in-memory concurrent hash map, and where the key will be your client ID. Okay, client ID will be key, and what would be the value would be your request count. Okay, so from this user, from user ABC, how many requests came till now, like 3, 4, 5, something like that, and window start time, that from 10 o'clock to 10 o'clock 1 minute. Okay, these many requests have come. Okay, so for each request check if the current time is within the active window. Okay, like in 1 minute he can send 100 requests. So from 10 o'clock to 10 o'clock 1 minute he can send 100 requests. When the time changes, like from 10 o'clock 1 to 10 o'clock 2 minute, okay, so in that case the counter will again reset, and he can send more requests as well. Okay, but above 100, no, we will just will not accept request from him. Okay, or we will slow down the response to him. So, and there are different algorithms. Okay, so this is the one which I said, that one is the fixed window, right, from 10 o'clock to 10 o'clock 1. But you will see multiple algorithms here, sliding window and everything, right? So in this video only we will see all those things. Now now so for each request, check the current time is within the active window. If yes, increment the counter. Okay, like from 10 o'clock 1 to 10 o'clock 2 minutes, you can send 100 requests, and currently 3 requests only came. Now fourth one came, so you will increase that counter value, variable value. If the counter exceeds limit, reject the request, and with HTTP 429. HTTP 429 code is too many requests. Now otherwise allow the request. If the window has expired, reset the counter. Okay, now so Java code, if you see here, so this is rate limit is the class. Okay, we will take, as I told you, that we will maintain two things. The first one is count, second one is Windows start. So Windows start is log type, count is atomic integer. Why atomic integer? You can have multiple servers. Okay, so let's say I am a user and I am sending request to your and you have 3 servers for your application. Okay, so I am sending request to your application. First request came to server 1, so counter variable increased to 1. Okay, then second request go to server 2. Okay, so count, so there on that server it is only 1 only, right? Or at the same time, if I am changing, so it should be atomic integer. Now by the way, you should have only 1 copy, so every time, or just use the Redis, okay, global cache. So we'll store these values there, then you will not have these problems. We'll discuss all these scenarios in this video. Now so this is the constructor. Here you will just pass the time, so we'll assign that time to Windows start time, and then your count will be initially new atomic 1, integer 1. Now as I told you, as he said that he will be using ConcurrentHashMap, where key will be your client ID and value will be your Windows start time and count variable. So now so this is the allow function, okay, for this particular user. So he is implementing per user. Okay, so he is sending the user, he is just calculating the current time. Okay, and then for that particular user, he will be checking whether this user already exists or not. Okay, if the value is null, it means the user is not exist right now, till now. Okay, and then it's a Windows start time is also greater than 60. Okay, in that case it is a new request, right? So just create a new rate limit now. Otherwise whatever you have in that count variable, just increment its value and then return that value. Okay, the value is rate limit object only. So now at the end, if your this rate limit count is greater than is less than equal to 100, then return true, otherwise return false. Okay, so allow that user, otherwise don't allow. So this is the normal code. Okay, this much only. So let me remove this, and you can see now the code. Okay, after this so now senior software engineer, what he would be answering for this. See, you should have knowledge on these things, okay, coding part, but apart from that you should have knowledge on these things also. Okay, you should say these things as well. So senior software engineer, he would be saying that in-memory solution works only for single instance. Okay, in production, request may hit multiple application server behind the load balancer, so each instance would maintain its own counter, resulting in an inaccurate limits. I told you, right? You have 3 servers, all 3 server will have the counter variable, so all 3 will maintain its own count, right? So it will be inaccurate limits. So now I would move the counter to Redis, because it provides shared state, atomic operation, time to leave support, and high performance. Okay, so Redis cache, global Redis cache will be using. So architecture will say, so now the architecture for that is something like this. So client will send the request, it will go to load balancer, then from there API gateway, and you will implement your Redis on API gateway level. Okay, because so on the earlier only you just discard the request. Okay, and then if it is allowing, then go to application server, that request will go your servers. So this will be flow. Client request will go to Redis. Okay, in Redis you will have some INCR, expire, this kind of functions. It will check it's whether it is valid or not, or it will check that it will increment the value. Okay, it will automatically handle all those things. And then if count is less than equal to 100, okay, then it will allow, otherwise it will send HTTP 429 too many request code. So now for example, INCR user 123, okay, and then expire user 123 60 seconds. So in for 60 seconds, after 60 seconds, again count variable will initialize to 0. Now both operations are usually executed atomically using Lua script. Okay, so this is the Lua script we use in the Redis, and it will automatically execute all these things. Okay, now advantages: centralized counter. Okay, now you have one centralized counter, you don't have each server counter variable, and then shared across instances, very fast atomic expiration and horizontal scaling as well. Principal engineer, what he will be answering, that expected answer from principal engineer would be, at Amazon scale, a rate limiter is a distributed platform service. Okay, so the goals are low latency, high availability, correctness, and minimal operational overhead. I would place a rate limiter at the API gateway or edge layer to reject excess traffic before it reaches to the backend services. He is also saying the same thing. Okay, API gateway level or edge layer. Edge layer means your CDN, and CDN will have multiple edge servers, right? So there. I have discussed all these things in my system design videos, so just go there and see in detail. So Route 53, now we are talking here about Route 53, right? So what is Route 53? It is just the AWS service, okay, DNS service. Route 53 is a managed DNS domain name server provided by service provided by AWS. It is translated a human readable domain name like www.example.com into an IP address that computer used to find servers. Okay, so Route 53 will send request to global load balancer. From there it will go to API gateway, and then from there it will go to distributed Redis cluster. Okay, not one Redis cache, just Redis cluster, so that if one will be down, request will go to another one. You will have a replica of a Redis cache there, and after that if it allows, then it will go to multiple application cluster, where you will have a multiple cluster of the application, okay, replicas and everything. So now important consideration here is, see, you are having millions of users. Okay, here we are talking about architect point of view. So millions of user, multiple availability zone. Okay, then multi-region deployment, Redis cluster, consistent hashing, replication, failover, then observability, circuit breaker, and then graceful degradation. So all these things I have discussed in my earlier videos in detail. Now follow-up 1. So now we will be discussing here around 10 follow-up questions. Okay, so follow-up 1 will be fixed window versus sliding window, what you will be using. So what first we will see what is fixed window, what is sliding window, and then we will see answer from all three persons perspective. So now fixed window is a fixed window divides time into fixed interval, okay, every 1 minute, let's say. So once the limit is reached in the window, all additional requests are blocked until the next window starts. So for example, 100 requests allowed from 10 o'clock 0 to 10 o'clock 1 minute, and then counter reset at 10 o'clock 1 minute, okay, from 1 to 2 minutes. Now sliding window, a sliding window always looks at the last 60 minutes, okay, 60 seconds from the current request time instead of fixed interval. So let's say 60 seconds we have configure the limit, so last 60 seconds. So for example, see, this provides a smoother rate limiting and avoids sudden burst at window boundaries. Okay, so example, 10 o'clock 1 minute 30 second counts request made between 30 second to 1 o'clock 30 seconds. So like it is, so let's say this is your 0, this is your 1, this is your 2, this is your 3, so this is 1 minute, right? So here if you are here 0.5 and you are here 1.5, so it will maintain for this as well. Okay, so now let's see what software engineer would be answering for this question, which is the fixed window or sliding window. So see, software engineers will say that fixed window is easy. Okay, fixed window is easy and sliding window is slightly complex, because you have to keep track of last 1 minute, let's say, okay, that time. So now fixed window will use low memory, sliding window will use higher memory. Okay, then fixed window allow burst, and sliding window prevent burst. What is burst? So see, let's say this is your 0, okay, this is your 0, and this is your 1 minute. Okay, so now here I can allow 100 requests per minute, let's say my application, okay, and then this 2 will start from here. So you have not got any request till here, and then suddenly 100 requests, let's say your system got here. okay, and then suddenly at this starting also 100 request your application got from that particular user. So it means that within 1 second you got 200 requests, right? 200 requests you got, but that is incorrect, right? Because your system should allow 100 requests in 1 minute, but here in 2 seconds your system is getting 200 requests, and your system is allowing that also, because from this algorithm fixed window, this is correct, right? This one will not happen in sliding window, because in sliding window when you are at this second, okay, it will check last 60-minute count also, okay. So this is the burst, but this is limited one, okay. So that is also fine, because only at max you will allow 200 requests, that's it, right? So you will configure according to that. So answer would be fixed window is simple and memory efficient, but request at the boundary of 2 windows can exceed the intended rate, okay, from 100 to 200. Sliding window provides smoother limiting by considering the previous window, making it more accurate. So he will be using sliding window here. Now senior software engineer, what he would be saying that for most APIs I would prefer sliding window because it provided fairer throttling and avoids sudden burst. Okay. So throttling, what is throttling here? Throttling means controlling or limiting how many requests a user can send in a given time. To prevent the system from being overloaded. Okay, so now for example, if an API allows 100 requests per minute and 101st request is delayed or rejected, okay, so this protects the server from ensuring fair usage of all the user. What architect would say? So architect would say that the decision depends on the traffic pattern. For customer facing APIs, I would use sliding window. For internal services where simplicity and throughput matters more, fixed window is often sufficient, so he will be using hybrid. Now follow-up question 2 would be token bucket versus leaky bucket. Okay, so I told you we have multiple algorithms, so fixed window, sliding window, token buckets, leaky bucket, all these things I have already discussed in my earlier video, okay, system design video, rate limiting. So now let's see what is token bucket first. A token bucket adds token to a bucket at a fixed rate, like 10 tokens per second. Okay, you will be having one bucket here, and then 10 tokens are 10 tokens you are per second you are putting there. Okay. Each request uses 1 token, and if no tokens left, the request is rejected. So there would be some capacity of this bucket. Okay, let's say 100 tokens I can have. So if there is no token in the bucket, then we will just reject the request, otherwise we will accept it. So for example, if the bucket has 100 tokens, a user can send 100 requests at once, burst to traffic, then must wait for new tokens to add it. And tokens are adding like 10 tokens per second, something like that. Leaky bucket, a leaky bucket processes request at a fixed steady rate, like water leaking from a bucket. Now let's say you have a leakage here in this bucket. Okay, so that leakage means water will be flowing from a fixed rate, like right from that leakage, not like 100 requests came and you have 100 tokens here in the bucket, so it will serve all 100 requests at once. No, it will just go with some fixed rate. Okay, so if requests arrive too quickly, the bucket becomes full. The extra requests are rejected. Okay, for example, even if 100 requests arrive at once, the system processes them gradually, okay, with its own speed. That is 10 requests per second, creating a smooth and consistent flow. So that is token bucket and leaky bucket. So now what software engineer will answer for this? See, token bucket is allowing burst, right? So for example, token added to every second, and then request consume token, no token, then it will reject. So leaky bucket, smooth output, he will say. Okay, so what is the leaky bucket diagram? So something like this: incoming requests are coming, okay, it will add it into a queue, and then fixed process rate. Okay, from fixed rate, it is that water is flowing, right? So that similar way. Now what senior software engineer will say here, for API I would choose token bucket, because user often send burst traffic that should be allowed within a limit. Okay, because user is sending burst traffic, then that is also needed, right? So we are anyways allowing it in a limit. More than 200 we are not allowing it. 100 is the limit, right? So that is fine. Architect would say that Amazon commonly favor token bucket for customer API because it balances burst handling and sustained rate control. So now follow-up 3 question would be distributed rate limiting. Okay, What if you have a distributed server? Then how will you do your rate limiting thing there? So software engineer will say store counter in a Redis instead of local memory. What senior software engineer will say, use Redis cluster with atomic operations, so all application instances share consistent counters. That is all we have already discussed earlier. Now what architect will say here, use consistent hashing, replication, failover, local caching where appropriate to reduce latency while maintaining correctness. See, he is seeing from higher level, okay? He is seeing the complete architecture of the organization, okay, for multiple projects. So that's why he has added all these things: consistent hashing, replication, okay, failover. Why consistent hashing here? Let's say, see, why consistent hashing? So instead of sending requests to random Redis server, use hashing so that same user request always go to the same request node, okay? Otherwise each node will have its own counter variable and will have the different values, okay? So you have to then combine all the means you have to synchronize all those values, right? So why to do that? Just use consistent hashing. From this user request will go to that server only. This keeps the user counter accurate and distribute load evenly, okay? Replication. So why replication? Keep one or more copies, replicas of the each Redis node. If the primary node fails, the replica already has the data and can continue serving request. Okay, then failover. So if Redis server crashes, automatically switch to a healthy replica. That's why we have created replicas, right? So without manual intervention, automatically it will just switch there automatically. This ensures the rate limiter continues working with minimal downtime. Now local caching, so store rarely changing data, like rate limiting configuration, okay, 100. I will not change every time, okay, that is the one time thing. So this kind of thing just store in a local cache, so he has not to go to global cache, global Redis cache cluster and then fetch from there. It will take some time, right? So you can store all these kind of things to a local cache only in that server itself, inside the application memory, instead of fetching from Redis every time. This reduces latency, lower Redis loads, while user counter remains in Redis for correctness. Follow-up 4. So that's the Redis implementation. How will you implement the Redis? Okay, so software engineer will use this kind of script like incr key, expire key 60. Okay, what senior software engineer will say, I would use Lua script to increment and expiration happens automatically. So if you are using Lua script, it is maintaining everything automatically, okay, by himself. So now architect will say, for higher accuracy, I would use Redis sorted set, okay, Z set we call it, Z set, sorted set, for sliding window implementation, because they store timestamp for each request and count on the request from last 60 seconds, okay, so which is meeting your requirement, correct? I would use Redis Lua script to perform all Redis operation, remove old request count and add new request automatically, preventing race condition when multiple requests arrive simultaneously. So now fifth question would be multi-region support, okay? So for multi-region support, let's say your application serving globally, you're serving your application globally, so you will have multiple regions. If your server is in one region, okay, and from some another region user is requesting something, so it will take some time, so you will just create new server there itself, so it will be nearer to that user and the request will get served from that server itself, okay? So that's why multi-region support. So software engineer would say that I would keep a separate limiter in each region, okay? So in each region he will keep a separate limiter. What senior software engineer will say, I would define whether the limit should be regional or global. First he will define the limit, okay? Since global consistency increases latency, of course, okay, it will go to global cache and then read value from there, so it will take some time. So first he will determine that whether it is really important or not. Architect will say global rate limiting is difficult because user request counts are stored on multiple servers in different region and updates takes time to synchronize. Okay, so replication delay, of course, right? So I usually enforce rate limits within each region for better performance. If the business require one strict global limit across all region, I would use a global replicated data store, accepting the extra latency. We cannot do anything, then we have to accept this extra latency. So now follow-up question 6 would be race condition, okay? So race condition, multiple threads are changing the value, right? So software engineer will say that multiple threads may increment the same counter simultaneously. Solution: use AtomicInteger in Java or Redis INCR because they increment the counter safely as a single atomic operation. Okay, now senior software engineer, he will say that Redis atomic command or Lua script eliminate race condition. If multiple Redis commands need to run together, then, like for example, what check limit increment counter set expiry, okay, so use Lua scripts so they execute as one atomic operation, preventing inconsistent results. So it will handle automatically. It will run all these operations as one atomic operation. Now architect will say that distributed locking is rarely needed, okay, because lock will take time, okay, it will increase the latency. So prefer atomic primitives because locks reduce throughput. Avoid locking the entire system unless absolutely necessary. Instead, the fast atomic operations like AtomicInteger, Redis INCR, or Lua script because they are simpler, faster, and allow more requests to be processed concurrently. Now, follow-up 7 would be related to thread safety. Okay, the software engineer will say that I will be using ConcurrentHashMap or AtomicInteger. Senior software engineer will say that he will avoid synchronized blocks because they reduce scalability. Okay, then architect will say favor lock-free algorithm. He is not in favor of putting the distributed lock. Okay, instead of that, he will be using atomic operation to maximize concurrency. Now, follow-up 8 would be burst traffic. Okay, suddenly the traffic came. Software engineer will say that token bucket naturally handles burst. Okay, means auto. At the end, he will handle 100 burst, 200 burst. That's it. Okay, it will not allow more than that. This is the boundary conditions. So when traffic is low, the bucket keeps filling with tokens until it reaches its maximum capacity. Each incoming request use one token. During a sudden traffic spike, the application can use all the stored tokens, allowing many requests to pass immediately without waiting. This is what happens, right? Now, senior software engineer would say that I would configure bucket capacity separately from refill rate to absorb a short traffic spike. Okay, he will that bucket capacity he will configure separately. Now, I would set how many requests are allowed in a burst bucket size separately from how fast new tokens are added refill rate. This gives better control over burst traffic. Now, architect would say that combine token bucket with auto scaling queue and back pressure to protect downstream system during sudden traffic surges. Now, what is back pressure? So, back pressure means telling client or upstream services to slow down when the system is overloaded. Okay, instead of allowing unlimited requests that could crash the application. So now, follow-up 8 would be related to API gateway integration. So software engineer will say that client request will go to API gateway. From there, he will configure his rate limiter there, and then it will go to backend service. Senior software engineer will say that reject request at the gateway before they consume backend resources, right? And architect would say the gateway should perform authentication, authorization, rate limiting, logging, and metrics. So backend service remain focused on business logic. Now the 10th one, the last one is not last one, last second I think, right? 12th, oh, last third. So 10th one is saying memory optimization. Okay, so software engineer use TTL, so inactive users are removed automatically. Senior software engineer will say that store only active user and avoid retaining stale counters. And architect will say that use compact key format, efficient data structure sharding, eviction policies to control memory usage at scale. Architect will say will say about complete architecture, right, around that. Now follow-up 11 will be TTL handling. So how you will time to leave, you will handle this in a Redis. Okay, so software engineer will say he will use expire key 60. In 60 seconds it will expire that particular count value. Now senior software engineer will say always set the TTL when creating the key, so expired counters are cleaned up automatically. And what architect will say, choose TTL that matches the rate limiting window and monitor key expiration behavior to avoid unnecessary memory growth. Now the last one is monitoring. Okay, so software engineer, what he will monitor: allow request, rejecting request, and then request rate and response time. Senior software engineer will also monitor these additionally. Okay, what Redis latency, Redis memory, Redis CPU, error rate, HTTP 4 to 9%. Okay, now what principal software engineer architect will do here? At platform scale, I would build dashboard and alert around. Okay, alerts and dashboards. So in that dashboard, what he will show, request per second, Okay, in 1 second how many requests are coming. Allow versus throttled request, P95, P99. Okay, so what is P95, P99? Rate limiting latency. So like it is measures how long the rate limiter takes to process. P99 means 95% of the request and then complete within that time, while P99 means 99% of the request and how many time it has taken. So we are talking here only about the slowest 5% or 1%. Okay, and then Redis CPU, memory, and replication lag, and key eviction rate, API gateway 429 trends, and after that regional traffic distribution, failover events, all these things, and then cost, Redis infrastructure. Okay, cost, who will see the cost? Architect. Now I would also define SLO. What is SLO? SLO is service layer objectives. For example, rate limiter latency under a few milliseconds. Okay, and conduct load test and validate behavior under burst traffic and node failure. So SLO stands for service layer objective, and SLO is the target performance or reliability goal that service aims to achieve. Okay, so that I will achieve this, like for example availability, yeah, 99.99% our system would be up. So this is written in SLO. This is their SLO, service layer objective. Latency, 95% of the request should respond in under 200 millisecond, and error rate less than 0.1% of the request should fail. Okay, so related terms, so SLI, SLO, SLA, all are related. SLI is indicator.